This video is going to go over exponential growth and decay. Okay, so it says situations when a quantity is increasing or decreasing exponentially are known as exponential growth or decay. Examples of exponential growth are population growth or growth of bacteria. Examples of exponential decay are depreciation of value of items, decay of radioactive substances. Okay, so first we're going to do an example of exponential growth. It says an entomologist monitoring an insect plague notices that the affected area by the insects is given by AN equals 1,000 times 2 to the 0.1 times n hectares, where n is the number of weeks after the initial observation. So question A says find the original affected area. So original kind of goes with initial. It's when no weeks have gone by. So that's like when n is 0. So A of 0 is 1,000 times 2 to the 0.1 times 0. Now 0.1 times 0 is just 0. And 2 to the 0 is 1. So that's just 1,000 times 1, or in other words, just 1,000. And our units would be hectares, which I think we just put as ha. Okay, for B, find the affected area after 4 weeks. We'll just do I. 4 weeks, that's when n is 4, so we put that in there. A of 4 after 4 weeks is 1,000 times 2 to the 0.1 times 4, or in other words, 0.4. And that equals 1,319.5 hectares. And you probably could have rounded that to the nearest whole number, given that it's more than 3 significant figures. So part 2, we just this time put n is 8. So A8 equals 1,000 times 2 to the 0.8, which is 1,741 hectares. And then finally, part 3. This is when n equals 20. So A of 20 is 1,000 times 2 to the, now think about this, it's 0.1 times 20, that's just 2 to the 2. And 2 squared is 4, so it just becomes 4,000 hectares. So part C is draw the graph of AN against n. So I've given you a grid here. So let's draw it. When n was 0, we had 1,000 hectares. So I should draw it right here. But when n is 4, we have 1,300, so it's around here. When n is 8, 1,700. And when n is 20, we have all the way up to 4,000. So it's kind of this shape. Times 2 to the 0.1 n. Now I probably should label my axes. So that would make this down here n and this a. And now we can use that to predict other values. For instance, after 14 weeks, we could guess how much there would be, how much area is affected. So let's say 2,000, 700 or so. So that could be a way to use that function. Exponential decay. When a diesel electric generator is switched off, the current dies away according to the formula CT equals 20 times 0.5 to the T amps, where T is the time in seconds after the generator has been switched off. Find the current at 0, 1, 2, and 3 seconds. When T is 0, the current of 0 is 20 times 0.5 to the 0, which is just 20. Now, and that should be amps. When T is 1, now instead of writing T equals 1, I can just write C of 1, because that value in there tells me that T is 1. That's enough. Okay, that becomes 20 times 0.5 to the 1, so it's just half of 20, which is 10 amps. So when C is 2, that's 20 times 0.5 squared. Now hopefully you know a half squared is just a quarter. So a quarter of 20 is 5. And C3 is 20 times 0.5 cubed, which really is just a half of 5, which is 2.5. Because you can see they're all halving each time, because we're timesing by another half. So question B, what current flowed through the generator at the instant it was switched off? Okay, so in other words, what current was going through the generator at that initial time, at time is 0? That's this one here actually. So it's just 20 amps. So they're asking us for us to understand what that 20 means. Plot the graph of the current using the information above, or the values that we've got, in other words. Okay, when time was 0, the current was 20. At time 1, the current was 10. At time 2, 5. At time 3, 2.5. So what do we expect to happen after that? We expect it to keep halving, so it'd be about there, there, there. So that looks like an exponential function. So let's go just downwards and graph that. So that there is C equals 20 times 0.5 to the T. So we should probably label our axes. This one down here must be T, and this one up here is C. Use your graph or technology to find out how long it takes for the current to reach 4 amps. So let's use the graph. 4 would be about here. So if we go across, I'd say it's at about 2.5 seconds. I would say it takes 2.5 seconds to reach 4 amps. You can do it by technology, by using nsolve. So you can, in your GDC, you can do nsolve, and you'll find that under menu algebra numerical solve if you're using your calculator. And you put in the equation, except your C is 4. So your current is 4. So you put in 4 equals 20 times 0.5 to the, now you could make it X or T, and I think you need to do comma X, as in solve it for X. And then enter, and you should get an answer that's approximately 2.5. The weight of radioactive remaining after T years is given by WT equals WO times 3 to the negative 0.001 T grams. So what's happening at the original weight? That's when T is 0. So we would say W0 equals, well, just W0 times 3 to the negative 0.001 times 0, which is just 3 to the 0. So I get W0 equals W0, because 3 to the 0 is 1. Now that was a little bit of a trick question. It's actually just, it should have said find an expression for the original weight. In other words, W0 is the original weight. Now for part B, it says find the percentage remaining after 100 years. Notice they're asking for a percentage, because we don't know the exact amount, because we have this W0. We don't know what W0 is. Therefore, we can never know the exact amount. But we can know the percentage of the original amount. So, remaining after 100 years, that's when t is 100. So, Wt is going to equal W0 times 3 to the negative 0.001 times 100. Or in other words, W0 times 3 to the negative 0.1, which equals 0.896 times WO, because that became that decimal. So what does that mean? The new weight equals 0.896 times WO, or in other words, times the original, which equals 89.6% times WO, which is 89.6% of the original. So in other words, 89.6% remains.